Hey everyone, so today we're going to talk about the squeeze theorem, which is sometimes called the sandwich theorem or the pinching theorem. Okay, and what we're going to use this for is we're going to use this to find difficult functions limits. Okay, so perhaps we can use this as a tool. If we have some function that it's not easy to find its limit, we can use other functions near it or around it, specifically above and below, to help us find the limit for that function. So it all kind of goes off of this picture on the right here, which here's what we can tell. We have this function h of x, okay, which is above. We have a function f of x, which is below. And then we have this function that's in between. Specifically, we're going to call it g of x here. And we notice it's in between everywhere, especially right at a. It's exactly in between, okay? And we hope that if we're going to do this problem, h of x and f of x, these are hopefully things we can easily find the limit for. Okay, so h of x and f of x, those above and below, we hopefully can find what those limits are, because g of x is that in-between function that maybe is difficult to find the limit of. Okay, so if for all x values near a, so let's say like this whole area, if I know that g of x is between f of x and h of x, right? That's what that inequality says. So if g of x is in between, and I know that x approaches a, as x approaches a, I have the function limit of L, and as x approaches a for h of x, I also approach L. Okay, notice here, I'm approaching this value of L. I'm approaching this value of L. Then I can also say by the squeeze theorem that the limit as x approaches a of g of x would be L. Okay, so again, if I know a function g is always in between, okay, this is the in-between guy. If it's in between f of x and h of x, then I know that if f of x approaches L near a and h of x approaches L, then g of x approaches L. Now, obviously, this is a lot of letters, and I want to kind of give you a clear, like, what's a real-world situation for this. So what if we talked about basketball? So for example, okay, if I talk about this guy, Mike, okay, Mike, okay, he scores the least number of points on a team. Okay, so every single game, I look at the scorebook, Mike has the least amount of points every time. You know, he's working his hardest, he's just not scoring the highest. Okay, then there's this guy, Jordan. Okay, he scores the highest number of points on the team every single game. Open the scorebook, Jordan's in there. He's got the most points every single game. Pretty good at basketball. All right. So then there's this other member. Okay, his name is Stan. Okay, and Stan consistently is always in between Mike and Jordan. So no matter what Mike scores, Stan always scores more than him. So Mike scores the least. So Stan at least goes above Mike, but he always scores less than Jordan because Jordan scores the most in basketball here. So another way you could write this, if you're talking about scoring in basketball, put them in order. Mike scores the least. Stan scores in between them every single time. If Mike has 15 points and Jordan has 25 points, then Stan scored somewhere in between. Maybe he scored 20 points. Okay, so that's another way to write this with inequalities. Okay, so again, think of this. I want you to think he's kind of like the g of x function, right? So we don't know anything about Stan's exact point values that he usually scores, but we know he's in between this f of x, Mike, and this h of x, Jordan. Stan is in between here. So we know some info about this guy. We know some info about this. but we're not totally sure on how many points Stan typically scores, except that it's in between. So let's say we have a game. Okay, first game of the season. Mike scored 15 points. Remember, he scores the least. Jordan, he actually scored 15 points. Okay, and I want to clarify here, when I said less than and greater than, I should have said equal to. So Mike scores the least number or equal to the least, and Jordan scores the most or equal to the most. Okay, notice these less than or equal to, greater than or equal to signs here. Okay, if Mike scored 15 and he scores the least, and Jordan scores 15 and he scores the most, and we know that Stan is always in between, what can we conclude, guys? Stan must have scored 15 points. Excuse me. So that's what's really going on here, guys. We're talking about a middle function, and here's kind of that real world scenario, right? If we know the least and greater kind of limits of some function, and we know some function is in between, such as Stan in this case, then we know how many points he scored. If we squeeze it down to between 15 and 15, our only choice is 15. Okay, so how we're going to do this here, I'm going to shrink this down. Sorry, I'm writing so much in this little area. Okay, we're going to find the limits of the two squeezing theorems squeezing functions, fxn for function, and if they're the same, then we have the limit of our middle function. Okay, so we're going to find the limit of the top and the bottom functions, and if they're the same limit, by the squeeze theorem, we know that the middle function will also have that limit. Okay, so we're actually going to try number 2 first. Okay, so take a look at number 2. We have 4x minus 9. We have h of x, which is in between 4x minus 9 and x squared minus 4x plus 7. Okay, so this is that in-between function for x is greater than or equal to 0. Use the squeeze theorem to find the value as x approaches 4 of h of x. So again, we don't even know what h of x is. Could be a polynomial, could be a log, we have no clue. But it's some function that's specifically in between, let's call these f of x and h of, no, we're not going to call it h of x. How about k of x? Because h of x is already used here. Okay, so let's actually find the limit. So as x approaches 4, well, what happens as x approaches 4 for 4x minus 9? Well, 4 times 4 is 16. Minus 9 is 7. Okay, and then what about the limit as x approaches 4 of x squared minus 4x plus 7? Okay, this would give me 4 squared minus 4 times 4 plus 7, which is, again, 7. So here's what I know, right? The limit as x approaches 4 of 4x minus 9 is equal to 7. Okay, that guy is less than or equal to h of x. And h of x is less than the limit as x approaches 4 of x squared minus 4x plus 7, which was also 7, meaning, if you guys see the big picture here, h of x is between 7 and 7, or it must be 7 itself. So first of all, this says use it to find the value. We know right now the value is 7. Okay, so this would be the end of the problem. Just for formality's sake and because we're learning it today, I'm going to write down the sentence because sometimes it does say justify and we want to be able to write down a justification here. So let me write the justification. Okay, so here's what we would write. Since 4x minus 9 is less than or equal to h of x, which is less than or equal to x squared minus 4x plus 7, and the limit as x approached 4 of 4x minus 9 was 7. I meant to say equals. which was less than or equal to the limit as x approach 4 of h of x, which is less than or equal to the limit as x approaches 4 of x squared minus 4x plus 7, which was 7. Okay, by the squeeze theorem, THM for theorem, the limit as x approaches 4 of h of x, this unknown function, we can conclude is 7. Oh, I meant to write, I'm sorry, this should say the limit as x approaches 4 up here of h of x. I'm sorry about that. So again, pause if you need to here. Since h of x is in between these two functions, and the limit of the first function was 7, the limit of the bigger function was 7 as well, and that limit was in between, then the limit must also be 7 of h of x as x approaches 4. Okay, so we're going to finish up with number 1 actually. So again, pause if you need to. We're going to go back up to here. So number 1 gives us m of x, which is the absolute value, so that's this guy. Okay, m of x. And then we've got k of x is 0. So you'll notice this function is right here. K of x is 0. And you'll notice that this 1 minus qx, we don't really know what q of x is, but 1 minus q of x is always in between. Do you guys see that? So it's always below m of x, and it's always above y equals 0. Okay, as we approach 0, okay, notice, as we approach 0, okay, what's our limit? Well, we should already be able to tell that the limit as we approach, I'll use a different color here, the limit for m of x as we approach 0 from either side is 0, and the limit of 0 as we approach 0 is 0. So we already kind of know what's going on here in terms of the function. And again, what I just said out loud, you could write it if you want. The limit as x approaches 0 of m of x is 0, right? Because I get closer to 0 from the left and the right. The limit as x approaches 0 of k of x, which again is just 0. What's the limit of 0? It would be 0. Okay, so how do we know that this q of x is equal to 1? Well, let's kind of figure out what's going on here. We're going to try to start writing our sentence here for the squeeze theorem. It says explain. Okay, so since k of x, that was the littlest function, is less than or equal to that middle function, which was 1 minus q of x, which is less than or equal to m of x. That was that absolute value or the biggest function. Okay, small, medium, big. And we know, we just wrote this down, the limit as x approaches 0 of k of x is 0, which must mean that it's less than or equal to the limit of 1 minus q of x, which is less than or equal to the limit as x approaches 0 of m of x, which is also 0. So again, notice 0 is less than or equal to the limit, which is less than or equal to 0. Again, think back to when Mike and Jordan both scored 15 points. Stan also had to score 15. So in this case, if something's between 0 and 0, it must also be 0. So by the squeeze theorem, we know that that middle function, or 1 minus q of x, is equal to 0. So yay, that's pretty much all we got, except notice, and there's just one little trick here at the end, guys. It wants to know why limit of just q of x is equal to 1. And you could probably pretty quickly see here, you could probably pretty quickly see here why this is going to translate into q of x is equal to 1. 1 minus 1 is 0. Let me show you here kind of how we would manipulate this. So I'll do this in blue. So for our final step, how do we get this guy to say q of x is equal to 1? Remember, our properties of limits, we can split up this into the limit as x approaches 0 of 1 minus the limit as x approaches 0 of q of x is equal to 0. The limit of a constant is just itself. We can add over this limit to the other side, of our function. So now I have 1 is equal to the limit as x approaches 0 of q of x. Okay, I'll write that a little bit nicer. Sorry, this is very sloppy. So again, this was equal to 1. And then I added this function to the other side. And so now I have the limit as x approaches 0 of q of x is equal to 1. And that's what we wanted to show. Okay, and that's about it. We showed by the squeeze theorem why that's true. We explained and we're able to use that graph. And then number 2 is kind of that traditional problem you might see where we're just plugging in, we're doing that direct substitution with functions we know, 4x minus 9, x squared minus 4x plus 7. Those are functions that are easy to evaluate. In that middle function, despite being unknown, we do know something specifically about the limit as x approaches 4. Okay, so that's it, guys, on squeeze theorem. Thanks so much for watching, and please let me know if you have any questions.